Hello, today I'll be talking about Littlewood's model, which is a probabilistic model similar to Newsvendor that is slightly different in like the context which it's discussed. And so in Newsvendor, if we were choosing what quantity to supply to have available, here we already have a set capacity, like there's a set number of seats in an airplane or rooms in a hotel, and we're deciding how many to supply to each customer class. And so a customer class is a group of customers that are willing to pay a certain price with some demand distribution or willingness to buy distribution. um, right? And so we're basically breaking the customers into different classes and charging them different prices. For example, with the airlines, when you buy months in advance, you're a leisure customer, um, maybe planning on vacation. You have some willingness to change flights a little to go for a cheaper one. You're looking through all the options and choosing the cheapest one. So the airlines have to compete with each other to offer lower prices in order to attract that consumer, right? Versus the day before the flight, if the flight is almost full and they only have a couple seats left, they're going to charge really high price for those tickets because it's likely that someone will come along willing to pay for it. Even if not everyone is, they'll have enough people pay that high price to fill up the airplane and ultimately give them more revenue, right? So it's like, how do you balance trying to fill every seat, but also trying to charge the highest price possible? Well, the solution is dynamic pricing. You change the price over time, right? So this will make more sense once we look into the actual model, right? So the main parameter is C, which is our capacity available. That um, is a input to the model, and like changing that would like drastically change the nature of your scenario, right? Um, D1 would be the demand of class 1 customers. So um, customers who are willing to pay price P1, right? And then let's say D2 is the random variable, the demand distribution at price P2 for P2 less than P1. We'll have it in descending order. 1 means that's the higher price. So like these are so D1 would be like the customers who are paying day of for the flight versus D2 would be the customers paying when the flight's still empty. And then like the core assumption is that um, the D2, the lower price demand is experienced first. Or yeah, that is kind of an assumption, or is kind of like a definition. If you think about, like, we could just always switch the subscripts so that this makes the case, but just the important part is like that they're not occurring at the same time. We're not able to charge both of these prices at the same time. We have to choose at different times which price, right? And so in the simple case, we're going to be charging P2 until a certain time, and then we switch to charging P1. Um, yeah, and so our decision is um, the decision variable K, which is the number of seats, or let's say the maximum number of seats to sell at P2. So like once you hit, so if we think of like number of seats sold, once you hit K, then you're going to be charging P1 for the remaining few seats. And then once you hit C, you can't charge anymore because you've sold all the seats. And then before you hit K, you're charging price P2, right? And the first customer is going to pay P2, etc. Once you get to the K plus 1 customer, then they're going to have to pay that higher price. Um, in other words, we can look at like C minus K, which would be the number of seats reserved for class 1 customers, like at price 1. So basically, if we know K, we know C minus K. Like, so they're giving us the same information, but we call C minus K Y, or the protection level. So like most of the time when we're phrasing it, we're going to be talking about the protection level Y. But K makes it like a little easier to see how we get to this next part, which is the objective, right? Whenever we have a optimization problem, when we're maximizing or minimizing a function, we want to write out what that function is. So in this case, it's going to be to maximize revenue, which we'll say is R of K. And so that's going to be P2 times the number of class 2 customers plus P1 times the number of class 1 customers, right? So we want to write a function so that if we choose K, we can calculate the revenue. And, well, revenue depends on these random variables for demand. So we're actually going to maximize the expected revenue, right? And then we want to find the expected number of class 2 customers. So if we think about the two cases, like D2 is how many customers arrive. If D2 is less than K, then we sell D2 customers, right? If D2 is greater than K, then all those customers that come after the kth customer are going to be charged P1, or they're not going to get a ticket, right? So we're only going to allow at most K people into class 2. So like we look at these two cases, what does this mean? Like, well, whichever one is smaller is the number of customers, right? So P2 times, and let's go ahead and put in the expected value of minimum D2 and K. That's how many class 2 customers come. If we get more than K class 2 customers come, it's still cut off at K. That's what our decision of K means. And then P1, again, we're not just multiplying to D1 because it also depends on our capacity, right? So we have P1 times the expected value of minimum D1. If only D1 customers come, then, and that's like 0, then we'll have 0 come, right? But we're also limited by the capacity, which would be C minus how many class 2 customers there were. Yeah, how many class 2 customers there were. And so we already wrote that as min D2K, right? So it's C minus min D2K. And yeah, this is a little more complicated to find than Newsvendor, how we've written it out, but really not that much. The only complicating part is that. So like we could think about going through the same proof as last time, but let's take a different approach just to show you a different optimization technique, right? So in last time we had concave optimization, like we just set the first derivative equal to 0 and assume that the second derivative was always positive. If we don't, then we have multiple local extrema, right? So we can just set the first derivative equal to 0 to get some of the local extrema, some of the local maximum minimum. Like we have some function like this, we would be able to find the nearest one of these extreme points by setting first derivative equal to 0. But even more simpler than that is we can look at the first order condition for a local extrema. So instead of looking at the second derivative, we're just looking at the first derivative and saying that's getting us close to an extrema, right? So like basically a local extrema would have f prime of x equal to 0, and then f prime of x, let's substitute in the definition. That's the limit as delta goes to 0, f of x plus delta minus f of x over delta, right? And we're setting this equal to 0. So when you're setting it equal to 0, really, just this term is what is being set equal to 0, right? So we have a first order condition for optimum is f x plus delta minus f of x equals to 0. And in this case, our function is r of k instead of f of x, right? So let's write out r of k plus delta minus r of k and set this equal to 0. But anyways, when we get this, we're going to have p2 times the difference when we plug in k plus delta at first, and then we subtract when we plug in just k, right? So we have expected value of min d2 k plus delta minus expected value of min d2 k plus p1 times expected value of min d1 c minus min d2 k plus delta. And then this is a little long, so I'll just write it down here. Expected value of min d1 c minus min d2 comma k. And that's in parentheses being multiplied to the p1, right? But if we just think about this whole thing, that's going to be 0 if the minimum's d2, right? If and this delta is approaching 0, right? So we have we're still taking the limit as delta approaches 0, right? So if d2 is less than k, then that thing comes out to 0. Otherwise, it's going to come out to k plus delta minus k. Otherwise, that one's going to be the minimum, right? And that just equals delta, right? So our expected value is the probability of this second case, which is d2 greater than k. The equality could be put on either side since in the notation above I had continuous demand, and here we still have continuous demand because I'm assuming there's some d2 value that exactly equals k. So anyways, our expression comes out as p2 times delta times the probability of that value, right? Expected value, where you're going to take the value delta times the probability, which is d2 greater than k, and then we think about this right side in blue, and that's P1 times whatever this difference in expected value comes out to. A lot of the time, these two random variables are going to be the same and the difference is 0, but we can think, like, in what case are we going to end up with the k plus delta over here and the k over there, right? So if d1 is the minimum, or d1 is less than c minus min d2 k plus delta, then we're going to get expected value of d1 minus expected value of d1, right? And so that whole thing comes out as 0. If we get d2 to be the minimum of, right, so d2 is less than k, then we're going to get rid of this k plus delta, and we're just going to have d2 on both, right? And we're subtracting the same thing. So really, we want to have the case where d2 is greater than k and d1 is greater than c minus min d2 k. Or yeah, you don't have to have the delta here because we're just comparing it to this, right? And in this case, what are we going to get for this expression? Well, over here, we're going to get c minus k plus delta, parentheses, And then over here, we're going to be subtracting C minus K. And so then we're going to be left up with negative delta. So pretty similar to the other, but now we have negative sign in front. And we'll write out this probability, right? So our expected value is going to be this value times the probability of this case plus 0 times the probability of the other cases. And again, like you can think about having signs here just to make it mutually exclusive. But of course, we know that the equals case is probability 0 as well because they're a continuous random variable for D2 and D1, right? So we have P1 times negative delta, the probability D2 is greater than K, and D1 is greater than C minus min D2 K. And so this is like probability D2 is greater than K, and the probability D1 is greater than C minus min D2 K, given that D2 is greater than or equal to K, right? These, we're not assuming independence, but we can still, say that this is the same because we have the condition taken in on our right side, right? And when D2 is greater than or equal to K, that means the minimum of D2 and K is just K, like always, right? So this is just probability D2 greater than or equal to K times probability D1 is greater than C minus K, negative delta. And then, like, this obviously is our right side over here. So let's just go back to black and plug in the whole expression, right? So RK plus delta minus RK equals P2 delta probability D2 is greater than K plus P, we'll just change it to minus since it's plus and negative, minus P1 delta probability D2 is greater than or equal to K, make this one equal as well, sure. And then probability D1 is greater than or equal to C minus K. And we want to set this whole expression equal to 0 because that's our first order condition. We're setting the first derivative equal to 0, and then we want to be able to solve for just one of these probabilities so that we get it in like an easier form to write with. Already both of them have probability D2 greater than or equal to K. But like you do the algebra and you'll get probability D1 is greater than or equal to C minus K equals P2 over P1, right? So basically both of those are present in that. So if you divide it out with a 0, you're not really losing information. Sometimes you would be like, but not here because we have it accounted for in the other case. And we're doing the as delta approaches 0. And so, really, you can think about now that we've set it equal to 0, this is our optimal K. This isn't true for all K that this equals 0. It's only true for the optimal K. And C is our parameter. There's no optimal C. C is just given. K is what the decision variable is like. So at the optimal K, we have this. And again, like our C minus K up here is the protection level Y. So C minus K star is the same as Y star. So that's why it's simpler to talk about the protection level, is because in our solution, we have the protection level versus if we had K, we would do C minus K, because this only depends on the demand distribution of D1. That's an incredible result, right? Even though we have two classes of customers with different demand functions, how many seats or how many rooms, how many items we should reserve for the class 1 customers depends solely on the demand distribution of class 1. Those higher price customers are where we need the information. We we need information about the distribution of those higher price customers, but not necessarily the lower price customers, because really our services are targeted towards that higher price customers, or rather our pricing scheme is targeted towards attracting more higher price customers. We can easily write this in terms of the CDF by doing the complement of this probability, right? Probability D1 less than or equal to Y star is the CDF of D1, and then we'd have to do 1 minus the probability, so 1 minus P2 over P1. And let's compare this result to our solution to a Newsvendor, which was probability D less than or equal to Q star, our CDF of D equals CS minus CP over CS plus CH. And let's recall what those parameters mean, right? So we're minimizing the expected value of our cost function, cost of a given demand and quantity, and that was CP times Q was the cost of procurement or production, and then we had CH times expected value of maximum 0 Q minus D. So that was the expected number of items held over, like number of overstocked items, items that were not sold during the period because the quantity on hand was greater than the demand, right? And then we had plus CS times the expected value of max 0 D minus Q, how many understocked there were, how many customers were turned away without having a product available because they were sold out. But here we have slightly different meaning to CS, right? And our CP is 0 since we have a fixed capacity and we're not paying anything for it, right? But now we have C of D1 and Y, right? So instead of Q, we're calling it Q minus, instead of Q minus D, we're calling it Y minus D1, but that's just changing the names of the variables. This result above still holds, right? So if we look at the cost of overage, that's our CH. In this scenario above, right, or when we're talking about D1 and Y, that's we made Y too high. We had to turn away a customer of the class 2 because we were reserving it for class 1, right? So for every 1 unit that we make Y too high, we would be losing out on revenue P2. So the cost of making the protection level too high is negative P2. We lost out on that revenue that we could have had from a class 2 customer. And then the cost of an underage is like how much we would be paying for setting the protection level too low. If we had to turn away a class 1 customer because we already sold that seat to a class 2 customer, right? So that's going to be the lost revenue that we could have made by selling it to a class 1 instead of selling it to a class 2, right? So it's going to be P1 minus P2. Very, yeah, like as like why is this one negative? This one's positive. Like the overage we're seeing, like actually making your protection level too high, you don't pay a positive cost. You actually pay a negative cost because you still got that revenue from customer 2. Versus in underage, we have a positive cost because you lost out on that price difference that you could have charged. Yeah, and so like putting that in terms of the critical ratio CS plus CP over CS plus CH, we have P1 minus P2 divided by P1 minus P2 minus P2. And then let's see how that equates to the same thing as up there. P1 minus P2 over P1 equals 1 minus P2 over P1. The same thing here. And then we see, I was just tripping in the explanation. We're having that be positive because of how we've defined CH, right? So relating these two problems together is not super obvious because like all the definitions are different, but really it is the same problem as Newsvendor. We took a little different approach to proving it, but it is the same problem. Instead of writing it like this, we could have written it like that. So um, we just have slightly different notation for what the variables are called, etc. But ultimately, we're just like setting a quantity that um, is available for purchase, um, right? And then um, let's do an example. I have these numbers written down. For example, when we have the capacity is, um, let's say 200 seats in a plane, and our price 2 is $200 to the customers that buy early, and our price 1 is $600 to the customers that buy later, and our demand 1 distribution, like the willingness of customers to pay price P1 after we've already sold the P2 seats, would be uniform 10 to 7, and then D2 would be uniform 100 to 200. So, like, potentially you could fill up the entire plane with just D2 customers. But really, as we saw in our result, our optimum value comes from probability D1 greater than or equal to Y star, probability D1 greater than or equal to Y star equals P2 over P1, the smaller price divided by the larger price. And so we're actually not even using this distribution of D2. We just need the distribution of D1, right? But anyways, our critical ratio P1 over P2, critical ratio is 200 over 600 equals 1/3, right? And then we want to find this probability using the CDF of D1, right? So that's going to give us our Y star. Our Y star equals 70 minus 1/3, 70 minus 10. And like you could write out the PDF, CDF more explicitly, but in Newsvendor, I did that for uniform. Like you can see because it's uniform, like this is how we get 1/3 from the end of the distribution, right? If we have like our CDF, right? We want this probability to be 1/3. Probability we're greater than or equal to Y star to be 1/3. So we can take this endpoint, which is 70, and subtract 1/3 the total range because it's uniform, right? And then that gets us to 50. So we would be reserving 50 seats for class 1 customers, and the other 150 could go to class 2 customers. And ultimately, this is not great because this 100 and this 10, like there's a good chance we're less than that 200 seats, right? So an airline would probably want to try changing these prices P1, P2 so that we have higher demands in both cases because we want to be able to fill the airplane more often. And that's where the next component comes in, right? If we want to do this even further, we'll look at n different demand classes and charge multiple different prices instead of just two, right? So let's generalize to n demand classes of customers that are willing to pay different price, right? So DI is the demand distribution or the willingness to pay at price PI. And last time we said they were conditional. Like here, when we have many of them, we do need to assume independence. And of course, we still have and sequence. Like we have the last one comes first, then the next one, then the next one, etc. Of DI distributions. And we have P1 is greater than P2, greater than or equal to Pn by definition, right? So this Pn is our smallest price. The first class of customers coming is class N, and they get the lowest price. Class 1 is still our most prioritized customer that pays the highest price, right? And so, like last time we had P2 over P1. Now if we're looking for our decision to be a sequence of protection levels, like vector, like multiple protection levels. Protection levels y1 star, y2 star, yn star, like how many to reserve for class I, right? Number to reserve for class I would be y star I. And then, like as in the last time, we're not really caring about this last one because that's probably going to be limited by our capacity. If we set all these equal to some capacity, then yn would just be the capacity minus all the ones before. But in the general case, what if we're selling a product that doesn't have the capacity, but we still think that the price can increase over time because it becomes more valuable for whatever reason. Like maybe just inflation, the price is increasing naturally. Or you're giving a discount to early buyers for a video game to try and encourage pre-orders or whatever. Like some scenario where you want to give early customers a discount, but you don't necessarily have a fixed capacity, right? Well, anyways, like last time we just had P2 over P1. Now we have Pi plus 1 over P1. So that's going to get us y star I. We want this to equal, instead of probability D1 greater than y star, right? Probability D1 greater than y star, we want to consider all the demand classes before it. So probability D1 greater than y star 1, and D1 plus D2 is at least y star 2, right? So this second protection level, you're reserving it for the second demand class and the first demand class because neither of those have happened yet. All the way until D1 plus D2 plus ... plus Dn is greater than or equal to y star, or let's not use Dn, sorry, let's use I minus 1, right? As we're saying, this ith protection level is for the ones before it, right? And so we only have n minus 1 protection levels. Or in other words, we could write this as probability d1 greater than y star 1, d1 plus d2 greater than y star 2, and then we sum over the j equals 1 to I minus 1, right? Or you could write that as summation of j less than I. Summing over the j that are less than I, we want to add the demand distribution of j and have that be greater than protection level for class I. Or in other words, if you're even more used to condensing it, right, we can say for all I that are or like for all k or for all L that are less than I, we want something to be true about this. So sum j equals 1 to L minus 1 of dj is greater than or equal to y star L for all L equals 1 to ... I. and that's, we want this probability to pi plus 1 over p1. Yeah, if that notation's a little confusing, just refer to the first line. Like, anyways, we just have that same ratio of the probability of the next class of customers over the class 1 customers that we're most prioritizing, right? And so if we think like, if we had a ton of demand classes and a limited capacity, then maybe we would want to reserve all the seats for like the first couple classes, and after class 3 we wouldn't have any seats offered to them. Like, there's a certain price that we wouldn't want to sell below that price, even if you buy far in advance, right? And so how can we get an exact solution to that? Well, in the continuous case, we have dynamic programming because we have this summation inside of the probability of this for all L between 1 and I. Right? You can turn that into constraints and maximize it. Or in the discrete case, you would have to do simulation, like because you can't get exactly equal to that value. So you'd have to find the next closest solution, doing Monte Carlo. But let's again, as like last time, we got a first order condition that we said was good enough, close enough to optimal solution, and actually, like in practice, it gets to that optimal solution. Like, the result we have from Newsvendor and Littlewood's model is accurate, even though how we derived it, we said there was some room for slight approximation, right? But anyways, how I'm going to explain how we do this is introduce more notation. An indicator variable, which is binary variable representing 1 when an event happens and 0 otherwise, right? So we can say b of j given y star. So y star is now our vector of all the y star 1 to y star n, and then d, which is now all of the demand distributions, right? Just to remind ourselves that this bj is a function of our y star selected and the d that's an input to the model, right? And we're going to have this equal to 1 if d1 is greater than y star 1, d1 plus d2 is greater than y star 2, etc. d1 plus dot 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 plus dj is greater than or equal to y star j minus 1 j, and then it's going to be 0 otherwise, right? 0 otherwise. And so now so basically we're referring to this thing. We want the expected value of this binary random variable to equal that for all the different j, right? So expected value of, yeah, why don't we just call this I instead of j, because I was using the j out there. I minus 1 I. And then expected value of p I y star comma d. We want that to be equal pi plus 1 over p1. And so how could we achieve this approximately? We can do an iterative method. So we can choose initial solution y0, right? And then go through k iterations to get yk. So we get each time we improve our y, and so after k iterations we get yk, and eventually we want that to be our solution that we go with, close to the optimal solution, right? And so one way we can make it approach the optimal solution is called stochastic gradient descent. So basically, we're walking down that first derivative, since we have multiple random variables or multiple variables within y star, right? We're taking the gradient with respect to y star, walking down closer to that local extrema. Like we have something like this in a multi-dimensional space, right? So if we had 3 dimensionals, look something like that, we're approaching some minimum. But now we have even more dimensions than that. You can't really visualize it, but basically if we were minimizing, we're traversing down to that minimum. If you phrase it as a maximization problem, which we did actually up here, then we're approaching up to that top point of the curve. Well, and anyways, like you don't have to visualize it that much. You just have to really see like we're going through different iterations of y to try to approach y star. And so our y of j at iteration k plus 1, so that's how are we going to choose our y for the next iteration? Yeah, or maybe we just save y for the y star for the optimal and y for the current iteration, right? So our current iteration, we have value y, k plus 1, and for each of them, we're going to set separately, right? So y is our vector. We want to know how to set each element of y at iteration k plus 1. Well, we're going to take the last iteration and then subtract by gamma k p I plus, or yeah, again, I switched to j over here because I have that written down. I pi plus 1 over p1, which is our target value, and then minus b, or yeah, maybe that one would be a y star because that's what we want for the optimal. And this is just what we get for a y generally, bi of y d, right? And then we're going to do that for all I in between 1 and n for all, right? And so gamma k we could set as, we call this the learning rate. That's another parameter that we're setting. So in addition to the parameters of the model, we have this parameter of our optimization. And basically we want to get to y star, right? So we want limit as k approaches infinity yi of k, right? We want that to come out to y star at index I. We want this to be optimal or pretty close to optimal, approximately optimal, right? And so the proof of this is by Robbins and Monroe, but anyways, their result is that this will approximately it will be approximately optimal, and it will converge, which means yk approaches yk plus 1 as k approaches infinity, right? Once we get to a very high iteration, we're no longer changing the y. The y is staying stable, right? And so that would be like the terminating condition of how many iterations we do. We iterate until our y value stops changing because we've approached that approximate optimal solution, right? So this thing means it's approximately optimal. This thing means it's converges. And again, this we could write as a limit again, right? But that sentence notation should be familiar too, right? But anyways, our convergence condition would be sum of k gamma k equals infinity, and sum of k gamma k squared is less than infinity. And so our learning rate, unlike neural network or just stochastic gradient descent for linear regression, it's subscripted by k. We're changing it at each iteration. which you could always do in stochastic gradient descent, right? But now we're saying if you sum over all the iterations of this parameter gamma k, we want that to blow up. But if you do it squared, then it doesn't blow up, right? And so one k that makes this work, one gamma k that makes this work is just 1 over k. So at each iteration k, our learning rate is going to be 1 over k. So as we increase through k, right, this gamma k gets smaller. At iteration 1, it's just 1 over 1, 1. And so we're changing our solution, like, right, as we go from yk to yk plus 1, we're subtracting a big thing, right? But once we get to high levels of k, this term is approaching 0, right? It's 1 over k. So we're subtracting a smaller thing every time until we get to a stable value. But this component over here ensures that even though we're like terminating our iteration, we are each step approaching the optimal solution. We are going in the right direction. And like we have a data set, we can calculate bi of yd pretty simply. We're just looking at like that condition.